Okay, here's part 2 of what happens to the thermal energy during a phase change. And I redrew the heating cooling curve for water just so that I could fit the remaining part of the problem down here in this lower section. The question that we ended with in part 1 was how much heat is needed to raise 10 grams of negative 15 degree ice to 200 degree vapor, to 200 degree vapor. I made a little mistake here. Okay, how much heat is needed to raise 10 grams of negative 15 degree ice to 200 degree water vapor? That's the question. Okay, what do we know so far? We know that the temperature does not rise during this part and this part. Okay, what are those parts? What do they represent? Well, this first plateau represents where the ice is converting to liquid, right? And we know that at the microscopic level, the bonds are breaking. Okay? And what happens here where we have liquid water being converted to water vapor? Well, we know the bonds that are holding the water molecules close together in liquid form are breaking, and so those water molecules are now able to move farther away from each other and become vapor. Okay, so we have bond breakage. Now these bonds are intermolecular bonds known as hydrogen bonds. They're fairly weak. It's not like the H2O molecule itself is degenerating. It's just that the bonds that hold the H2O molecules attaching to other H2O molecules are breaking. So that's what's happening at those plateaus. Now the amount of thermal energy needed to do this, that's called latent heat. Latent heat. Latent heat is the amount of thermal energy needed to do this, to change the phase from one to another. But there's no temperature change, is there? Okay, so latent heat is the amount of thermal energy needed to change the phase. Okay? Now in the case of this one here, this is called the latent heat of fusion. The latent heat of fusion. We can just use L sub F for short. Latent heat of fusion is the heat needed to melt 1 gram of ice into 1 gram of liquid water. Okay? So the heat needed to melt 1 gram of 0 degree ice, I should say, to 0 degree liquid. Okay? And it turns out that there's a certain value for that of water. Okay? So for water, for H2O, that turns out to be about 334 joules of heat are required to raise 1 gram of 0 degree ice to 1 gram of 0 degree liquid water. That's the latent heat of fusion for water. Other materials, like for CO2 or for other compounds, other than water, they would have different values. This is just specific for water, and we're just looking at that for water right now because that's most familiar to us. this other plateau up here, it's a much wider plateau, isn't it? In fact, for water, if I were to draw this to better scale, this horizontal line here would be 7 times approximately wider than this horizontal line here. And that means that there's 7 times more latent heat energy needed in order to convert 1 gram of liquid water to 1 gram of water vapor at 100 degrees Celsius. Okay? So this is known as the latent heat of vaporization. Latent heat of vaporization. And we'll use the symbol capital LV, and let's do it for water. For water, that would be equal to approximately 2,260 joules of heat required to convert 1 gram of liquid water at 100 degrees to water vapor at 100 degrees. There's the latent heat of vaporization for water. Other materials like gold or CO2 or whatever, they would have different values for their latent heat of vaporization. Now, what does latent mean? It means underlying. It's not readily apparent, but we can see that there, even though the temperature isn't rising, there's still heat being added, because of those bonds breaking. Now, what I'm going to do is I'm going to take a piece of paper and lay that over the top so we can do a problem now. Okay, so there's maybe 2 pieces of paper so we don't see it underneath. Okay, so now let's do our problem. How much heat is needed to raise 10 grams of negative 15 degree ice to 200 degrees Celsius water vapor? Okay, like I said earlier, if we look from where we're starting at negative 15 degree ice to 200 degrees Celsius vapor, that's 5 steps. 1, 2, 3, 4, 5. So we're going to need to do 5 steps here. So step 1, that would be using good old MCAT. That's the heat needed. Remember, Q stands for heat, needed to raise negative 15 degree ice to 0 degree ice. Okay, and that's just good old MCAT. And we take the mass of the ice times the specific heat of the ice times the temperature change that the ice goes through. Okay? And what's the mass of the ice? We can just go ahead and put that here. The mass of the ice is 10 grams. I'll put that right here. Specific heat of the ice, that's not 4.18. Ice and water vapor are different phases than liquid water. Liquid water is 4.18, but ice is about 2.01. I'm just going to round it off to 2. So that's 2 joules per gram degree Celsius. So it's not 4.18 for the specific heat of ice. It's about 2.01. What is the temperature change that negative 15 degree ice went through? It went from negative 15 to 0. That's a temperature change of 15 degrees Celsius. Okay. If we do the math, just go ahead, and we really don't need a calculator for that, but anyway, I'll just do it anyway. 10 times 2 times 15, and we get 300. And since we're talking about heat needed, that would be in joules. So we need 300 joules in order to do step 1 for 10 grams of ice, excuse me. Okay? Now we need to go to step 2. Step 2 is where the ice, 0 degrees, is being melted to 0 degree liquid water. Now, there's no temperature change, so we cannot use MCAT, because MCAT has a delta T in it. And if delta T is 0, that would mean that we have 0 heat added, and we know that we don't. So this is a job for latent heat. Okay? The latent heat I'll just put, remember, for that, a fusion is 334 joules required for every 1 gram of 0 degree ice to change to 0 degree liquid. So we'll use that. And so therefore, to find the heat, we'll take the heat needed or required would be equal to the mass of the ice, or the water. It's going to be the same mass, times not the specific heat times delta T, but times the latent heat of fusion. Okay, so in this case it'd be 10 grams of ice times 334 joules per gram. Okay, and that would give us 3,340 joules of heat that needs to be added in order to convert 0 degree ice, 10 grams of it, to 0 degree liquid. And we continue with this process. Okay, the next step, step 3, is involves a temperature change, so we do use MCAT again. This would be the heat needed to take 0 degree liquid and convert it to 100 degree liquid. Okay, I'll just put little squiggles to represent the liquid. And we can go ahead then, that's equal to MCAT, but this time it's the mass of the water now, converted to water, times the specific heat of the water, times the temperature change that the water went through. Okay? And so that would be equal to 10 grams times 4.18, or 4.19, I don't care, it's 4.186 really, but, and then the temperature change would be, it's going from 0 to 100. So the temperature change is 100 degrees. So we get 100 times 4.18 is 418 times 10. So that would be 4,180. Okay? And that would be joules. Step 4. We're going from 100 degree liquid, converting it to 100 degree vapor. No temperature change there, so we can't use MCAT. We have to use the latent heat of vaporization, which is 2,260 joules for every gram. That's how many joules need to be absorbed to change 1 gram of 100 degree liquid water to 1 gram of 100 degree liquid steam. So therefore, the heat involved in this part would be the mass times the latent heat of vaporization, and the mass is 10 grams times 2260, and that's easy to multiply in your head, right? So it would be 22600 joules, 22,600. Look at the enormous amount of heat required to convert liquid water to vapor. Or if you're going the other way, if you're converting vapor to liquid water, that's how much heat for every gram, for 10 grams of it, of the vapor, would be released into the surroundings if that vapor was converted back to liquid. So it goes both ways. Last step, we need to look at this step up here. Step 5, we're going all the way to 200 degrees Celsius vapor. Now that involves a temperature change, right? Because we're going from 100 degree vapor to 200 degree vapor. So we can use MCAT. So what's the heat needed to take 100 degree vapor and convert it to 200 degree vapor? MCAT, right? Mass of the vapor times the specific heat of water vapor times the temperature change that the water vapor goes through. Okay? And now let's go ahead and plug our numbers in. We have 10 grams of mass. And remember, the specific heat for ice and for water vapor are about half of that of liquid water. So instead of 4.18, it's about 2. It's not exactly the same as for ice. It's a little bit less. Ice is 2.01. Vapor is like 1.99. But I'm going to round them both off to 2. And then the temperature change is going from 100 degrees vapor to 200 degree vapor. So that would be a temperature change of 100 degrees. Okay, and so we get 2,000 more joules of energy needed to be absorbed in order to do that step. Now to find the total heat added, we need to, that's the grand total, we need to add them all up. Okay? So I'll just get the old handy dandy calculator here, and that'll make it pretty straightforward. So 300 plus 3340 plus 4180 plus 22600 plus 2000. And we get a grand total of 32,420 joules. That's the total, the grand total. Grand total. And that's how to do a thermal energy problem where you have phase changes. And this one was just specifically for the phase changes in water, but if we had a different problem that involved maybe phase changes occurring in silver or gold or something like that, we could use the same procedure, similar procedure. Thank you, everybody. Bye.